Okay, Year 12, I'm going to go over quadratic equations with complex coefficients. We've already done this, but it's good to cover it again and remind ourselves of how to do it, but also we're going to learn another two methods for doing these. So the Grove goes through two methods for doing these. So method one, which we already know, but we know it with a little bit of a difference compared to what they do. And they get to this step down here, we do another step where we show that a squared plus b squared is a modulus, and we can use that. Method two is using Demoivre's theorem or Euler's formula, and method three is a graphical solution. So the first thing I'm going to do is do the easy ones. I'm not going to do a lot of these. I'm going to do question one. And if I look at question one, I've got this quadratic equation. Now, please remember, whenever you do a quadratic equation, there are two answers. There are always two answers. So we've got this quadratic equation. There will be two solutions to this. So the easiest way to try and solve this is to use a quadratic formula. So x is going to equal negative b, so negative 2i, plus or minus the square root of negative 2i squared, b squared, minus 4 times a times c. And it's all over 2a. So that's going to give me 2i plus or minus the square root. Now, negative 2 squared is going to be 4. I squared is negative 1, so it's going to be negative 4. Minus 4 times 3 is 12, all over 2, which is going to be 2i plus or minus negative 16 root negative 16 over 2, which is 2i plus or minus, the square root of 16 is 4, root negative 1, 4i, all over 2. And then I can cancel the 2, so I get I plus or minus 2i. So that'll give me, we'll do the first one, I minus 2i, negative I, or I plus 2i, 3i. So there's my answer to the first one. That was pretty easy. Now let's have a look at 2a. And we're going to have a look at this first method where we go, z squared equals I. Now, the first method I'm going to use is with our quadratics. So we can just quickly square root that and we get z equals plus or minus the square root of I. Now this is interesting. How am I going to do this? We've done this before when we've found the solution to different things. So we know that the answer to that is going to be a complex number. So we'll say let a plus I be some complex number equal the square root of I. And I'm just going to leave it as the square root of I because I'm going to square it, which will get rid of the positive and negative. Therefore, if I square both sides, I get a plus ib equals I, which gives me a squared plus 2abi plus I squared b squared will equal, I'm going to write this another way, I'm going to write that as 0 plus I, because it's a complex number, but it has no real part. So that gives me a squared, and this bit here is going to become negative b. So I'm going to put that together because they're both real parts, minus b squared, plus I times 2ab, and that equals 0 plus I. Now, if you remember from when we did this before, if we equate the real parts and then we equate the imaginary parts, there's a 1 there, I can get two equations and I can solve them simultaneously. So therefore we know that a squared minus b squared equals 0. And we know that 2ab equals 1. Now, we also know another thing. We know that for this complex number, that a squared plus b squared equals the modulus, and the modulus is 0 squared plus 1 squared square rooted. So the square root, I'm going to write this out even though I know that it's just 1, equals 1. Because we know that, think about it, I is this point here, and there it is, I, and it's a modulus of 1. We could even write it in cis form, and we're going to do that in a minute. But the reason I want you to do it this way is because it's much easier now to try and solve these two equations simultaneously than these two equations simultaneously. So, let's get rid of that. Now, so if I add these two together, I get 2a squared equals 1. Therefore, a squared equals a half. Therefore, a equals plus or minus 1 on root 2. Now, over here, I'm going to rewrite this quickly because I want to find what b is. So b equals 1 over 2a. So if a equals negative 1 on root 2, b equals a half 2 times negative 1 on root 2, which will give me 1 on negative 2 on root 2, multiplied by the reciprocal, and I get root 2 on negative 2, which, this is going to seem strange, if I multiply top and bottom by root 2, that'd give me, if I multiply by root 2, watch what's going to happen, because I'm going to do this again in a minute, and I'm not going to go through this again. I get 2 on top and I get 2 root 2 on the bottom, but that 2 on top would cancel with the 2 on the bottom, and I get negative 1 on root 2. Why did I want to write it that way? Because look at the way that a is written. And I want to keep it like that because it's going to be very easy later on. Now, if a equals positive 1 on root 2, then b equals 1 on 2 times 1 on root 2. And we're going to do the same thing. That's going to be 1 on 2 on root 2. I'm just going to slip down here to the bottom bit, which is just going to be 1 on root 2. So then I have, well, a plus ib is equal to minus 1 on root 2 minus 1 on root 2, or 1 on root 2 plus 1 on root 2. But I can write that in one go. A plus IB equals, if I take the negative out of that, I get 1 on root 2 plus 1 on root 2. Oh, sorry, I, forgot my I. So I just have plus or minus. So I'll write that properly, write the plus above. Plus or minus. Now that's important for later on. So there's the first one. There's my solution. Pretty easy. We've done it before and not that hard. Let's look at another way of doing it. So that's method 1. And they do that in the textbook. You can go and have a look. The only difference is that they do not use this, and I reckon that's a much easier way to go. So method 2. All right. We'll start from the same point. Z squared equals I, and we'll let Z equal some complex number, re to the I theta, where r is a modulus and e to the I theta gives me cis whatever the angle is. So Z squared equals re to the I theta all squared, which gives me Z squared equals r squared e to the I 2 theta. Now, Z squared also equals I. So that means r squared e to the I 2 theta equals I. Now, I, what is I? We already know it's this thing here, which means it's 1 cis pi on 2. 1 cis pi on 2. I don't need to write that. I can just see that the modulus is 1 and I can work out what the angle is. But anyway, so r equals the square root of the modulus, square root of 1, which equals plus or minus 1. But remember, this r in this thing here is a modulus, so it's always positive. So I can ignore that negative. So r is always greater than 0. So we can just say, oh, r is going to equal to 1. The modulus of our z is going to be 1. But now, over here, I've got, the argument of 2 theta, this is this bit up here, the argument of this is pi on 2. So I'll just write this, the argument of I. And we know that that's 2 theta equals pi on 2, which gives me pi on 4. Now, remember that the argument is the inverse tan of theta. And the inverse tan of theta, well, we'll get that argument, but it's positive. In this case, the argument, so, where else is it positive? Well, all stations to central. It's positive also in the third quadrant because we know we're going to get another answer. Well, in the third quadrant, that's pi down here. So it's minus pi plus pi on 4. So let me go down. Remember, we're minus pi, go forward that way. And we get theta equals pi on 4 and minus 3 pi on 4. Now, remember, we already know our solution. Here they are. But watch this. Therefore, z equals, well, what's our modulus? 1 cis pi on 4. Well, or the other root, we'll call that z1, we'll call this other root z2, is 1 cis minus 3 pi on 4. Well, cis pi on 4 is just going to be cos pi on 4 plus I sine pi on 4, which is 1 on root 2 plus 1 on root 2 I. And over here, z2, well, that's going to be cos minus 3 pi on 4 plus I sine minus 3 pi on 4. And we know that they're exactly the same as cos pi on 4 and sine pi on 4, but they're negative. So negative 1 on root 2 plus negative 1 on root 2i, which is exactly what we got before, negative 1 on root 2 minus 1 on root 2i. Same answer. So 2 methods for doing those. I kind of like method 2, but I'm going to be using method 1 because I've done it lots and lots. Now, before I show you method 3, I want to talk about something. So, for the graphical method, which is a really easy one, and we're going to be using a lot and when we come into it later, for the graphical method, we're going to be working on the presumption, and it's pretty important. The graphical method relies on the fact that roots on the complex plane are evenly spaced. And we'll talk about this when we do complex roots of unity later. Oh no, we're going to talk about it now. It's more important to talk about it now. In their method, they say they don't talk about it. So let's take z cubed equals 1. Now we know that there are going to be 3 solutions to this because it's a cubic. So if we do the cube root of 1, we get 1 straight away. So we get 1 and then we get, we think that that's all. But I want to take you down a path. There is a special rule that states, and it's no longer in 3 in it, but you need to know it, which is a cubed minus b cubed equals a minus b, a squared plus ab plus b cubed. So if we take this now and we say, oh, well, z cubed minus 1, well, that equals z minus 1, because 1 cubed is, and that's going to be z squared minus, plus 1z plus z squared plus z plus 1. So therefore, our solutions are z equals 1. So z equals 1, or we use a quadratic equation for this bit, which is, or z equals negative 1 plus or minus the square root of b squared, or 1 squared minus 4 times 1 over 2, which gives me minus 1 plus or minus the square root of negative 3 over 2, which gives me minus 1 plus or minus root 3i over 2. And note here, get back here. Note, and this is going to come up later, that these are complex conjugates. And what do I mean by that? Well, you should know from your third work, because it's minus 1 plus root 3, and I'll put that at minus 1 on 2 plus root 3 on 2i, or minus 1 on 2 minus root 3 on 2i. It's just the same thing, but subtracted and added. Now, let's think about this. An easier way to solve this, and this is what we're going to do, rather than going through that process, and that's this process here, and finding the 3 roots. Once we know z cubed equals 1, once we know 1 root, z equals 1 is one solution, but we know there are another 2 hiding out there. But we know they're evenly spaced. So if we go, let's look at the Argand diagram, and we get this 1 here. So we go, there's 1. There's 1 root. That's z first root, and it's 1. Well, the other 2 are going to be evenly spaced. So that means there's going to be 1 there and 1 there, and they're the same angle. And that angle is 120 degrees, because 360, because that's 120, doesn't look like I've drawn it badly, and that's 120. And 120 is 2 pi on 3. So this Z2 is same modulus, 1, so it's 1 cis 2 pi on 3. And this one, this Z3, Z3 is going to be 1 cis negative 2 pi on 3. Now remember, we already know what the 2 answers are. They're over here. Right? We've got 1 minus 1. But let's watch what happens when we get here. So we get Z1 equals 1. Z2 equals cis 2 pi on 3. Right, well, that's cos 2 pi on 3 plus I sine 2 pi on 3. Okay, well, cos 2 pi on 3, that's going to be negative the same as pi on 3, which is root half. So negative a half. And sine 2 pi on 3, okay, That's going to be root 3 on 2. Root 3 on 2 I, and that's negative as well. So I get negative, oh sorry, that's positive. It's positive in there because it's positive, so negative a half. I don't need to do that next line then because there it is. And there's our root over here. Can you see it's the same there? There it is, negative a half plus root 3 on 2I. And Z3 is cis negative 2 pi on 3. Well, that's exactly the same thing, except they're both negative. So you get cos negative 2 pi on 3 plus I sine negative 2 pi on 3. So you get negative a half minus root 3 on 2I, which is our same as our one over here. Now that's much easier. That's much, much easier to do. And you get them straight away. Let's take one more example. Let's just take z to the 4 equal to 1. Now, if I take z to the 4 equal to 1, you're going to think, oh, there's, plus or minus 1. They're the only two solutions. No, there are 4 solutions. And if I do it like this to really explain it to you, so that's z4 minus 1 equals 0, which means we're going to have difference of two squares, z squared minus 1 and z squared plus 1 equals 0, which means z squared equals 1, which means z equals plus or minus 1. So there are the two we notice straight away. But then we get z squared equals minus 1, and we get z equals plus or minus I. Now let's think about this again. Where are these? So if I draw the Argand diagram, if we just said, oh, where's the first one? Well, we know 1 is a solution, so there's Z1, and the other four, I'm going to use this one. So there's 1, and 90 degrees apart, there's the other one, and there's 90 degrees apart and the other one, there's the other one. So I get Z2, Z3, Z4, and I go, oh, they're all got the same modulus, so I'm going to get I, negative 1, and negative I. So the benefit of being able to see that when roots are equally spaced is you can pull out the other number of roots, however many there are, straight away. So now let's go to that very first question. And we'll do it the third way. So this is method 3. And we get z squared equals I. All right, so we're going to get, so this is question 2a. So there are two roots and they're equally spaced. Okay, so we don't let, the modulus of I equals 1. And the argument of I equals pi on 2. Right? So of this complex number, the modulus is 1, the arguments are 2. That's pretty obvious. So therefore, z squared equals cis pi on 2. You put the 1 there, right? Because it's just I. So therefore, one root is to get rid of that squared, I'll just raise it to a half. So I get 1 cis pi on 2 all to a half. Like I raised it to a half. Well, that'll give me 1 to the power of a half cis a half times pi on 2 by de Moivre's theorem, which will give me 1 cis pi on 4. Oh, 1 cis pi on 4. Oh, well, that's cos pi on 4 plus I sine pi on 4, which is 1 on root 2 plus 1 on root 2 I. Now, once you've got the first one, you don't have to go and do it again. You just go, well, they're equally spaced. So here's the first one, and it's 1 on root 2 across and 1 on root 2 up, and that's Z1, and that's pi on 4. Well, the other one is going to be 180 degrees, same modulus, and that's pretty obviously minus 1 on root 2 and minus 1 on root 2. Or you could just do cis minus 3 pi on 4. So the other root, Z2, which is this one, equals cis minus 3 pi on 4, because you know that they're equally spaced, and you just go 180 degrees or pi on 2 around, and you go, oh, there it is. So that is the graphical method for doing those. So let's just quickly recap. First of all, to solve complex quadratics, you can just use a quadratic formula. When you get something a little bit more complicated, you can use a squared, like equating the coefficients, a squared minus b squared and 2ab, but also know you can use a modulus, which is a squared plus b squared equals 1. And solving it, you get the answer, which tends to be the way that most people do them. Now that you know that z can be written as re to the I theta, you can use that and just realise that you're going to get two answers and you're going to get it in the third. You have to be noting of where it's going to be, if it's positive or negative. Or you can use this fact that roots are equally spaced. Once you find one, you can find all of them. Now, for all these quadratics, they're going to be 2, so they're all going to be pi degree, 180 degrees, pi radians apart. So once you find one, you just go the opposite. All right, good luck with those questions then.